Hello everyone, this is problem set number 4, problem 1. The PV diagram shows a cycle of a heat engine that uses 0.250 moles of an ideal gas with gamma equals 1.40, and gamma is a ratio of molar heat capacity. Process AB is adiabatic. For part A, find the pressure of the gas at point A. Okay, so let's write down our given information. I guess I could write it down right here. So givens, our moles, number of moles is 0.250. Ratio of molar heat capacity, that's gamma, is equal to 1.40. There's another thing this tells us, right? Because gamma is, or the value of ratio of molar heat capacity, which is gamma, this guy. That's a ratio of molar heat capacity. The values differ depending on what type of gas it is, right? If it's a monatomic gas or if it's a diatomic gas or polyatomic gas. So since it's given that the value is 1.40, it also tells us that therefore we're dealing with a diatomic gas. So therefore diatomic gas. Right, and we know that because the value for gamma, which is a ratio of molar heat capacity. 1.40 is a value for a diatomic gas. All right, and then it also tells us that from state A to state B, that is an adiabatic process. An adiabatic process. Okay. What does adiabatic mean? That just means that there's no heat transfer. So Q is 0. Q, heat transfer, is equal to 0. Okay, so we could start with solving the problem. So for part A, find the pressure of the gas at point A. All right. So we're looking for pressure at point A. I know that the process from state A to state B is adiabatic. So therefore, Q, heat transfer, is equal to 0, right? What else do I know for an adiabatic process? So in chapter 19.8, it tells us that P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma. Right, and that is for all adiabatic processes. Okay, and that's in chapter 19, section 8. Okay, so I'm going to use that information, that formula, to find PA. So using that, again, I go from A to B. So pressure at A times the volume at A to the power of gamma, which is the ratio of molar heat capacity, is equal to the pressure at B times the volume at B to the power of gamma, right? And we know the pressure at B, that's given in the problem right here in the PV diagram. It's 1.5 atm. The volume at B, I know, is 0.009, and the volume at A is 0.002. That's all given in the PV diagram. So I could plug that in and try to find the pressure for A. Okay, so PA is equal to pressure at B times the volume at B to the power of gamma divided by the volume of A to the power of gamma. Right? So I could rewrite this as pressure at B multiplied by volume at B divided by volume at A to the power of gamma. Okay? And that would be equal to the pressure at B. Again, we said according to the PV diagram is 1.5. So 1.5 ATM. Right, that's the units from the PV diagram for pressure, ATM. Multiplied by the volume at B, which is 0.009 cubic meters, divided by the volume at A, which is 0.002 cubic meters. All right. Oh, okay, and to the power of gamma, and it was given to us that gamma, or the ratio of molar heat capacity, is 1.40. So to the power of 1.40. All right, and if I plug that in my calculator, I would get that the pressure at A is equal to 12.3 ATM, right? Because my units cancel out here for cubic meters. All right, so that is the answer for part A. Okay. All right, moving on to part B. How much heat enters this gas per cycle and where does it happen? Okay. So it doesn't really tell us specifically where, which process that heat enters the system in the cycle and which process it leaves the cycle, right? We don't know if it's in the process where you go from state A to state B or state B to state C or state C to back to state A, right? I do know this is a heat engine, so this is a closed cycle process, right? Okay, so anyways, I'm going to use the ideal gas law. Which is PV equals nRT to find out where gas enters the system, or which part it enters the system and where it leaves the system. Okay, so let's start with process A to B, from state A to state B. Okay. Well, it tells us, right, it was a given that from state A to B, process AB is adiabatic, right? That's given in the problem. So because it's adiabatic, I already know there's no heat transfer, right? Because that is what adiabatic means. Q is equal to 0. There's no heat transfer in that process. So A to B is an adiabatic process. So there's no heat transfer and Q is equal to 0. Okay? Q means heat transfer, or heat transferred into the system. Okay. So that takes away one of three processes, right? Or, yeah, one of three segments of the cycle. All right, let's look at from B to C, the process from B to C. And I can see here that I'm looking at the PV diagram. From B to C, I go from this area, or that state, state B to state B, or to state C, right? And if you notice in the PV diagram, we maintain our pressure from state B to state C at 1.5 atm, right? So since we have a constant pressure, then I know that we've got an isobaric process. So B to C is an isobaric process. In other words, constant pressure from state B to state C. So, okay, I'm gonna put an underline. I'm looking at the ideal gas law formula right here. I'm gonna underline what's gonna be constant in an isobaric process, or a process with constant pressure. Obviously, the pressure is gonna be constant because it's constant pressure, right? That's what isobaric is. As well as N and R are constants. N is the value, is the number of moles, right? And that was given to us, it's 0.250. And R is just a constant, right? We know the value of that never changes. Okay. So if that's the case, we can say that if V over T is equal to NR over P, and these guys are constant on the right side of the equation, then we can say that VB over TB is equal to VC over TC. That's the volume at C over the temperature at C, right? Because they're both equal to this guy right here. And that's constant, it doesn't change. Okay. So just based on this formula, volume at B over temperature at B is equal to volume at C over temperature at C, we can see that since the volume decreases, right, at state B, we've got 0.009 cubic meters as our volume, and at state C, we've got 0.002 cubic meters as the volume at C. And based on this formula, we can see that if the volume decreases from B to C, right, I'll write that down. Since volume decreases from state B to state C, that's B to C, okay? Therefore, if VB over TB is equal to VC over TC, therefore, temperature decreases also from state B to C, right? Okay. And just to show that real quick, side note, let's say this is not actually the values, but let's just say VB over TB was 5 over 10, right? And VC over TC was that's just equal to 1/2, right? 5 over 10 is 1/2. And we see that if the volume from B to C decreases, or the value from B to C decreases, VB to VC decreases, then the value from TB to TC also decreases, right? And we see here that the volume at state B, actually decreases as it moves from state B to state C, right? So therefore, temperature decreases from state B to state C, okay? Okay, what about for state C to state A? Here that looks like we have constant volume as we move from state C to state A. So we have an isochoric process, right? So state B to state A, that's an isochoric process. And that is just a way of saying that volume did not change. We have constant volume from state B to state A, which is right here, 0.002, right, in the PV diagram. Okay. So now if we look at the ideal gas law for an isochoric process when volume is constant, I'm going to underline the constants in the ideal gas law, right? This time volume's constant. And like I said, N and R are always constant. So unlike the isobaric process, this time we've got P over T, pressure over temperature, is equal to N, or the amount of gas in moles, times R, the constant, divided by V, right, the volume. So this time, everything on the right side of the equation are constants. So therefore, we can say that the pressure at B over the temperature at B is equal to the pressure at, I'm sorry, not B. So therefore, we could say that the pressure at C, right, because this time we're going from state C to state A. Okay, so the pressure at C divided by the temperature at C is equal to the pressure at A divided by the temperature at A. Okay? And as we can see from the PV diagram, the pressure increases from state C as you go towards state A, right? Because obviously the pressure up here will be higher than 1.5 atm. And actually, we solved it in part A. It's 12.3 atm. Okay? So we can say that since pressure increases from state C to state A, therefore temperature increases from state C to state A, right? And that really tells us all we need to know about where heat enters the system, or where heat enters the gas during the cycle, and when heat leaves the gas during the cycle, right? Because here we could say, since temperature increases from state C to state A, I know that during this process from state C to state A, heat enters the system, thus temperature increases, right? So I'm going to use that information to answer part B. Again, what is part B? How much heat enters this gas per cycle, and where does it happen, right? Well, it happens from state C to state A in that process. Okay? So I'll answer that for part B right now. So looking at these guys, I could say that therefore heat enters the system, or enters the gas, right? Because that's their system, during the process from state C to A. From state C to state A. Okay? And that is part of my answer for part B. But it also asks us how much heat enters the gas, right? Okay, so we're going to get to that right now. Okay, so In order to find how much heat enters the gas from state C to state A, I will use the first law of thermo, okay? So first law of thermodynamics, okay? And that is Q, or heat transfer is equal to the work, is equal to the work by the system plus change in thermal energy, okay? All right. So again, I'm only right now, I'm looking from the process from state C to state A, because I know that's when heat enters the gas, right? And that's what I'm looking for part B. So from C to A, right here, what is the work of, how can we calculate work in a PV diagram? It's the area under the curve, right? And for an isochoric process, like we have here from state C to state A, it's a vertical line, so there's no area underneath that curve. So again, for all isochoric processes, or for constant volume like we have here, from state C to state A, work is 0. So since work is 0, I know that for state C to state A, I can simplify the first law of thermo equation to Q equals, so the work system, that's 0, right, is equal to the change in thermal energy. So Q is equal to delta ETH. Again, if you're curious why the work is 0, look at the PV diagram. There's no area underneath this curve. That's a vertical line, right? And work is calculated as the area underneath the curve. And we're only looking from state C to state A, like I mentioned multiple times. So, what else do we know? We know that for all processes, whether it's isochoric, isobaric, or isothermal, I know that my change in thermal temperature, or delta ETH, is also equal to N CV delta T, right? And N is obviously the number of moles. CV is the molar heat capacity for constant volume, right? This guy, that's the molar heat capacity for constant volume. And delta T is a change in temperature from state C to state A, okay? What else do I know about the molar heat capacity for constant volume? Remember, we're dealing with a diatomic gas, right? Right here. We're dealing with a diatomic gas, and we know that because the value for gamma was 1.40. And for the ratio of molar heat capacity for a diatomic gas, that value is 1.40. And that's something you should know, so that you could come to the conclusion that, oh yeah, that's a diatomic gas. Okay? So anyways, since we're dealing with a diatomic gas, I don't know what the value is for CV, but I know that for a diatomic gas, and this comes from chapter 18, section 4, which is heat capacities. Okay, I know that the value for molar heat capacity for constant volume for a diatomic gas is equal to 5/2R, okay? So that's something we should know or have in our cheat sheet, and that is CV for diatomic gas. Again, if you need to find the different values for CV for diatomic or monatomic or polyatomic gas, please check out chapter 18, section 4. You'll see it there. Okay. So back to our problem. Let's rewrite this as N. So instead of CV, I'm going to use 5, oops, I'll write that a little better. 5 over 2R, okay? And that just comes from this information that I mentioned. Times delta T, right? Okay. So I'm gonna remove the constant, 5 over 2 times N times R times delta T, right? Okay, well, guys, unfortunately, I was not given the temperature in this problem. So I need to find another way to keep going with this problem. How could I do that? All right, let's do a side mission, okay? I call this side mission number 1. And I'll use pink. No, I'm going to use brown for side missions, okay? Side mission number 1. Let's say we want the delta of our ideal gas law. PV equals nRT, right? So I got the delta PV is equal to the delta of nRT, yeah? Again, we're looking at the isochoric process from state C to state A. So it has a constant volume. So I'm going to take out the constant volume because this kind of works like a derivative, or you could bring the constants outside of the derivative. So I've got volume, since it's constant outside, and then delta P is equal to, what are constants here? N and R, right? So I'm going to also take them out. So nR delta T, okay? And I'm going to substitute this here, okay? So given that info, I'm going to put here 5 over 2, and instead of nR delta T, I'm going to use V delta P, right? Because that's equal to nR delta T. All right. Now I can solve this because I know the volume, right? It doesn't change. And I know the pressure. Pressure for state C and pressure for state A. And volume doesn't change since it's an isochoric process, so I also know that. So I'll plug that in. Let me look at the PV diagram again. So the volume from state C to state A is 0.002 cubic meters. And the pressure at state C is 1.5 atm. And the pressure at state A, we solved in part A, that's 12.3 atm. Awesome. Oh, another thing. In order to use this in this equation, I can't use it in atm. I have to convert it to pascals so that my units can come out to joules, because that's what I want for my heat transfer, right? My heat in joules. So another side mission number 2. I'm going to convert my pressure in state A that I found in part A, that's 12.3 atm. I'm going to use a conversion for that, right? That's something we should also know, that 1 atm is equal to 1.01 times 10 to the 5th pascals. Okay? And so that is equal to 1,242,300 pascals if you plug that in your calculator. Because our units ATM cancels out, right? Okay, and side mission number 3, I'm going to do the same for pressure at state C. And according to the PV diagram, that was 1.5. Okay, so 1.5 ATM, and then the conversion factor, 1 ATM, is equal to 1.01 times 10 to the 5th pascals. Right? So my pressure at state C in pascals is, plugging that in the calculator, 151,500 pascals. Okay? Cool. So that's what I'm going to use for delta P. All right, so I've got 5 over 2, and my volume is constant, and that is right here, 0.002 cubic meters. So 0.002 cubic meters times delta P. So that is, since we're going from state C to state A, right here, my state C to state A, so delta P would be PA minus PC, which is 1,242,300 pascals minus, I'm going to move this a little bit to the left so I can have more space. Okay, minus PC, which is the pressure at state C, 151,500 pascals. Okay. And if I plug that in my calculator, I would get that the answer is 5,454 pascals times cubic meter. Okay. And if you multiply these two units, you would get joules. And if you need to find out how to do that, I do show that in previous problems. So you can look at those videos as well. Okay, so therefore my answer is the heat entering the system from state C to state A is equal to 5,455. Sorry, that's 5,454 joules. Okay. I'm going to do that in red. So that is my answer for part B. All right. So moving on to part C. How much heat leaves this gas in a cycle and where does it occur? Okay. Well, I could look at this whole thing that I did earlier to figure out where heat leaves the cycle, the gas in the cycle, right? So I could see that, I know that from state A to state B, no heat transferred into the system, into or out of the system, right? Because Q is equal to 0. So I don't worry about that. I know that from state C to state A, temperature increased, right? From state C to state A. So if temperature increased, that means heat entered the system. I'm not going to worry about that because I just want to know where heat left the system. Oh, look, from state B to state C, temperature decreased from state B to state C. So I can say that in this process from state B to state C, heat left the gas or the system, right? And that's what I want to know in part B. How much heat leaves the gas and where does it occur? Cool. So let's do that. So for part C, okay, I'm going to say, again, I'm looking at this information that I deduced. Temperature during the process from state B to state C. Therefore, heat leaves the system or the gas during the process from state B to state C, right? Okay, awesome. I also know that state B to state C is an isobaric process, right? Because in the PV diagram, the pressure is constant from B to C. Okay. Well, when we're dealing with an isobaric process, I know that Q is equal to N Cp delta T, right? Actually, I'll write that in blue. So it's equal to N. I'll just rewrite that whole thing. Q is equal to N Cp delta T. Heat transfer is equal to moles times molar heat capacity for constant pressure, Cp, times delta T, which is change in temperature. Okay? And I should state that this is only true for an isobaric process. So only true when you're dealing with constant pressure. Okay, so if you're dealing with an isothermal process or isochoric process, you can't apply this formula right here. This is only true for an isobaric process. Okay? Awesome. So again, I'm going to try to rewrite this because I was not given Cp in this problem. I was not given the molar heat capacity for constant pressure. Okay? So how do I do that? And also, I don't know what delta T is. I don't know the temperature either in state A, state B, or state C, right? That wasn't given. So I'm going to do that the same way I did for part B right here. I'm going to use that delta PV equals nRT trick. So I'll do that here. Well, first of all, I don't know what is Cp, right? But what do I know? I do know that the ratio for molar heat capacity, which we call gamma, is equal to Cp over Cv. That is a formula that we should know. Okay, so if you don't have that in your cheat sheet, please write that down. And so this is the molar heat capacity for constant pressure. And here Cv is the molar heat capacity for constant volume, and gamma right here, that's the ratio of molar heat capacity. Okay, anyways, we know that gamma is equal to Cp over Cv. That is true. And that's just something we should have in our notes or cheat sheet, okay? So I'm going to, instead of Cp, I'm going to write that as N times, I'm going to say gamma times Cv, right? Because that's equal to Cp based on this formula. And then delta T. Delta T, okay? Since gamma is given as 1.40 in the problem, I'm going to take that out. It's a constant, right? So I'm going to put gamma N Cv delta T. What else do I know? Oh, I know that CV, right, is equal to 5 over 2R. We talked about it earlier. CV for a diatomic gas is equal to 5 over 2R. That's in chapter 18, section 4. All right, so I'm going to substitute CV for 5 over 2R. So equals gamma N times 5 over 2R instead of CV times delta T. All right. Again, I'm going to take out my constant, 5 over 2. So I've got 5 over 2 times gamma times N R delta T. Remember, if we use this delta PV equals nRT trick, we will find, and I'll just redo it, okay? I'm going to rewrite that again. So we've got side mission number 1 for part C, delta of PV equals nRT. This time, so delta PV is equal to delta nRT. This time from state B to state C, right? That's what we're dealing with. That is an isobaric process. So pressure this time is constant. So this time, since, from PVP, B to C, yeah, pressure is constant, right? So pressure is constant this time. I'm going to bring constant out, pressure times delta V, because volume changes from B to C, is equal to constant R, constant N, constant R times delta T, right? I just removed all the constants outside of the delta. Okay. So I'm going to substitute NR delta T, this time with P delta V, okay? Because this time we're dealing with constant pressure. So is equal to 5 over 2 times gamma times P delta V, okay? And that is equal to 5 over 2 times gamma times pressure, that's constant, times, this time I'm going from state B to state C, so volume at state C minus volume at state B, right? State B to state C, that's where I'm going from. Okay. So let's plug in our values. We know that gamma, that was given to us, that's 1.40. The pressure at state B and state C is given here as 1.5 ATM, right? It's constant. But again, when I plug it in here, I've got to I can't use ATM, I've got to use pascals. And 1.5 ATM is equal to 151,500 pascals, right? We did that in side mission number 3 in part B. Okay, so I will plug that in. That's 151,500 pascals times volume at C. According to the PV diagram, volume at C is 0.009. Sorry, no, the volume at C is 0.002 cubic meters, and the volume at B is 0.009 cubic meters. So I'll just plug those in. Okay, the volume at C is 0.002 cubic meters minus volume at B, which is 0.009 cubic meters. All right, and if I plug that in my calculator, I would get minus or negative 3,711.75 Pascal times cubic meters, okay? And if you multiply these two units, you get joules. So you get minus 3,711.75 joules as your Q from B to C, right? And that kind of makes sense, right? Since our heat transfer right here, we see that it has a negative sign. So that means heat is leaving the system, or leaving the gas. And that's what we're trying to find out in part C, where how much heat leaves the gas and where it leaves the gas. So we answered it, right? Heat leaves the gas during the process from B to C, since temperature decreases, and we calculated how much heat was left the gas. Negative 3,711.75 joules. Awesome, so that is part C. Okay. Now let's go to part D. Part D. How much work does this engine do in a cycle? All right. So what is the cycle? So the cycle starts at state A, and we have an adiabatic process going to state B, and then an adiabatic means, again, no heat transfer, right? That process had no heat transfer. And then we had, after that, an isobaric or constant pressure process from state B to state C. And after that, we had isochoric or constant volume process from state C back to state A. And that's just a closed loop system. It keeps going. All right. Okay, so anyways, part D, how much work does this engine do in one cycle? One complete cycle. From state A to state B to state C and back to state A. Right? Okay. So I'm going to use, actually I will use the first law of thermo to find that out. And the first law of thermo is heat transfer Q is equal to work done by the system plus the change in thermal energy, right? Also known as change in internal energy, delta ETH. Okay, what do I know about a heat engine or a closed cycle device? Okay, so I'll write that down here. I'll write it in red, I guess. So for heat engines, or otherwise known as a closed cycle device, at the end of a full cycle, the change in thermal energy is equal to 0. Okay. So delta H or delta ETH is equals 0. The change in thermal energy equals 0 for heat engines. Okay. I found that out from the lecture video for chapter 20. So then if that's the case, then this becomes 0, right? Because we're dealing with a heat engine. That's our problem. So then we can say that work out, right, is equal to Q, since since delta ETH equals 0. Okay, and that workout is just this is just the work done per cycle by the heat engine. Okay. So what is our heat transfer? In this problem, okay, so work out, that's equal to Q. In this problem, what is our heat transfer? We had three states, right? So we had the heat transfer from A to B, plus the heat transfer from B to C, plus the heat transfer from C to A. And the sum of all those heat transfers is equal to the total heat transfer, Q, right here. Okay? So Q is equal to the heat transfer from A to B plus the heat transfer from B to C plus the heat transfer from C to A, right? And that whole closed cycle process. Okay, well, we calculated all those, right, from in part B and part C. What is QAB? QAB is 0 because it was an adiabatic process from A to B, right? So I'll plug that in. That value is 0 plus, what is QBC? We solved for that, right? That was negative 3,711.75 joules. And that was negative because that's a heat leaving the system or leaving the gas. Plus QCA. What is QCA? We solved that in part B. Okay, that's 5,454 joules. So positive 5,454 joules. And that's the heat that was added to the gas. Heat that entered the gas, right? Okay, so if you plug that in your calculator, you would get that that is equal to 1,742.25 joules. And that is the workout. That is the work done. Oh, I'm going to use red for final answers. So that is part D, okay? And that is the work done by the heat engine in a cycle, which is what part D was asking for. How much work does this engine do in a cycle? Okay, cool. Now part E. What is the thermal efficiency of the engine? Okay. So for part E, we're looking for the thermal efficiency of the engine. For part E, we're actually looking for E. Again, what does efficiency mean? So efficiency that means how much heat put in the system or in the gas was converted to work. So how much of the heat put in the system, in this case it was gas, right? That's our system, is converted to work. So that's the amount of heat that was not wasted, that was put in the system that was not wasted and was converted to work. All right. And in chapter 20, section 2, we know that the formula for efficiency is equal to work out divided by heat transfer, or QH, the heat transfer that was added into the system. Heat added to the system, QH. All right, and another way of writing that is 1 minus heat leaving the system over heat added to the system. QC is a heat leaving the system. QH is heat added to the system, or added to the gas. All right, I'm writing this in blue so that hopefully that's something you guys have in your formula sheet. Okay. So, funny enough, we already calculated for everything here, really. Our workout, as we calculated in part D, right here, that is equal to 1,742.25 joules divided by the heat that entered the system, QH, which was our positive. That was right here in part B. And that is equal to 5,454 joules, okay? And if you plug that in the calculator, that is equal to 0.3194. And the units cancel out, so there's no units for efficiency, right? So our final answer for part E, which is asking for the thermal efficiency of the engine, right? So our final answer is that the thermal efficiency of the engine is 31.9%. Okay, so that is the final answer for part E. And that was kind of a long problem, but I hope that was somewhat clear to you guys. And again, if you guys need help with understanding why this unit, Pascal times cubic meter, can turn into joules, please look at my previous videos. I do cover that stuff in every video, but since this was already a long video and I've repeated that from problem set number 1 to problem set number 3, I'm not going to do that anymore for problem set number 4 going forward. But if you guys would like me to do that, let me know in the comments and I'll make sure to do that. Okay, hope that